Welcome to Sachin Study Tech. Today topic is heap trees, priority queues. Heap trees, also known as heaps, are specialized tree-based data structure commonly used to implement priority queues. Heap is a complete binary tree that satisfies the heap property. So what is meant by complete binary tree? So now you can see here. So what is meant by binary tree? What is meant by complete binary tree? What is meant by full binary tree? So first you can see what is meant by binary tree. Binary tree means each and every node having at most two children. So now you can see here at most the node is there is no left child and right child. This is also a binary tree. So here you can see this is also a binary tree. You can see this is also a binary tree. Here it is also a binary tree. Okay, so you can see here this node having 0 children. So at most 2 children. Each and every node having at most 2 children. So it is 0 children or 1 children, that may be a right or left children. Here the node having 2 children. So these all are binary trees. But here it is not a binary tree. Here you can see this node having for example it is not a binary tree because this node having 2 children but this node having 3 children. So each and every node having at most 2 children only, that is called as a binary tree. So it is not a binary tree. So what is meant by complete binary tree? Complete binary tree means here having at most 2 power h to 2 power h plus 1 minus 1 number of nodes. So what is the meaning of this one? 2 power h? H means height of the tree. So here full binary tree means, so full binary tree having the number of nodes 2 power h plus 1 minus 1 number of nodes. So for example here full binary tree, what is meant by full binary tree? Here it is, for example I am taking only one node. Here how many number of nodes is there in full binary tree? Here 2 power h plus 1 minus 1. So there is no left and right child, so the level is 0, so that here it is h value is 0 plus 1 minus 1. That means 2 power 1, that 2 minus 1, here only one node is there. Here the full binary tree is, so this is full binary tree. For example here it is not a full binary tree. Full binary tree means then having the number of nodes are 2 power h plus 1 minus 1. For example you can see here, okay, so only height of the tree is 1, that means 2 power h value is 1, so that value 2 power 1 plus 1, that is 4 minus 1 3, but here only 2 nodes is there, so that it is not a complete full binary tree. Okay, now here you can see, so the height is 1, so that 1 plus 1 minus 1, here it is 4 minus 1, that is 3 number of nodes is there. So this is a full binary tree. So what is the relation between full binary tree and complete binary tree? The full binary tree having 2 power h plus 1 minus 1 number of nodes, but complete binary tree having 2 power h to 2 power h plus 1 minus 1 number of nodes. That means full binary tree is a complete binary tree, but complete binary tree may or may not be a full binary tree. So here you can see this is a complete binary tree, but it is not a full binary tree. Here you can see full binary tree means each and every tree having 2 power h plus 1 minus 1 number of nodes, but here height of the tree is 1, right? 2 power 1 plus 1, that is 2 power 2, 4 minus 1, that is 3, but here having only 2 nodes, but it is not a full binary tree, but still it is a complete binary tree. So that is the meaning. So complete binary tree means the tree is filled from left to right. So this is a complete binary tree. Here this is also a complete binary tree. For example, here it is 1, 2, 3. Here it is also complete binary tree. For example, here you can see it is not a complete binary tree because here left is empty. So we have to fill from left to right only. So complete binary tree is a binary tree in which all levels except possible last are completely filled. That means how to fill from left to right only. So it is not a complete binary tree. It is a complete binary tree. It is also a complete binary tree. It is also a complete binary tree. So full binary tree is a complete binary tree, but complete binary tree may or may not be a full binary tree. Now we can see here it is a full binary tree. Okay, this tree having 2 power h plus 1 minus 1 number of nodes because level is 1, right? 2 power 1 plus 1, that is 2 power 2, 4 minus 1, 3 nodes is there. So it is a full binary tree. So full binary tree, it is also a complete binary tree. Now you can see here it is a complete binary tree. Okay, complete binary tree, but it is not a full binary tree. Okay, it is not a full binary tree. This is a complete binary tree. It is also a complete binary tree. Okay, now here it is 1, for example 3, it is also a complete binary tree. 2, 1, 4, 8, it is also a complete binary tree. But here you can see 2, here 1, it is not a complete binary tree. For example 1, 2, 3, here it is 4, it is not a complete binary tree because here it can filled from left to right. So you have to fill this node and you can fill this one, but here it is not a complete binary tree, right? So complete binary tree, so heap trees are complete binary tree and also follows the heap property. So heap property, it is a min-heap or max-heap. Min-heap and max-heap. So heap tree must satisfy two properties. One is the tree must be a complete binary tree and also satisfies heap property, that is either it is a min-heap or max-heap. Now you can see min-heap means min-heap is a complete binary tree where every parent node value less than or equal to the value of its children. So what is the meaning of here? Here it is min-heap means the parent node less than or equal to child. So this is the min-heap. So what is the meaning of that? For example, here you can see the parent node is the minimum when compared to its children. Now you can see here it is a min-heap, right? So there is no left and right children, then you cannot compare with the children's. So this is the min-heap. Okay, maybe it is also a max-heap also because there is no left and right children's. So we are not comparing with any children. So there is no children here. This is a max-heap also. So for example, here you can see this is it a min-heap? No, it is not a min-heap. Min-heap means the parent less than or equals to children. So here the parent is 2, the children is 1. So it is not a min-heap. So that here you can see 1 and 2. So this is a min-heap. Right? For example, here it is a 4, it is also min-heap. For example, here it is 8, it is also min-heap. So it is 9, it is also a min-heap. Min-heap means here you can see it is a complete binary tree and also satisfy the min-heap property. So min-heap property means this is the parent node. So here these are the children's the parent less than or equal to children. So the condition is true, right? Here also this is the parent. Here the 2 4 is the children. Here also how can represent the min-heap commonly represented. Here the heap is represented in array format. Here you can see, so index is 0, here the index is 1, here index is 2 and index is 3 and index is 4. Now you can see here can represented, here it is a 1 and the level order it can maintain, here it is a 2, here it is a 4, right, here it is a 8, here it is 9. So index is 0 1, array index starts with 0 1 2 and 3 and 4. Now how you can check, here it is, this is a parent. So how to find out, here it is a parent of I, that value is I minus 1 by 2. So this is the parent node. For example, how to find out the parent of I here. For example, I value is 0 here, 0 minus 1 by 2, that means minus 0.5, but you have to consider only positive rounded value, floor value you have to consider, that is a 0. So here it is a 0, right? You have to find out left children of this I, left child, how can find out, 2I plus 1. So I value is 0, right? 2 into 0, that is 0 plus 1, so 1. So this is the left child of this I. So how can find out right child of I, that is 2I plus 2. So I value is 0, right? 2 into 0, 0 plus 2, that is 2. So this is the right child of I. So here also you can see here, for example, if you want to find the parent of this one, so how to find out the parent of 8? Now you can see here it is a 3, right? So how to find out the parent of 3? Here I value is 3, right? So 3 minus 1 by 2, that is equal to 2 by 2, that is 1. Here you can see this is the parent. Now here you can see this is the 1, this is the parent. So 8, the parent of 8 is 2, right? 2. Okay, like that I have to find out. For example, if you want to find out the left child of 2 and right child of 2, that means the I value is 1, right? Here 2 into 1 plus 1, that is 3. So this is the left child. Right child you have to find out, right child, 2 into I value is 1 plus 2, that is equal to 4. So this is the right child. Okay, like that you have to find out the parent of any I, and also have to find out the left child and right child of that particular node. And what is meant by max-heap? Max-heap means the parent greater than or equal to child. That means here this is also a max-heap. For example, here it is 1 and 0. This is also a max-heap, right? 8 4 2, this is also max-heap. And also here it can satisfy, here it can see. So first it is a complete binary tree, and also you can check the heap property. Now it is a complete binary tree, right? Then is it a max heap? You can see here it is satisfy the max heap property. Parent greater than or equal to child. Yes, the parent is a maximum when compared to its children's. Okay, and also here also you can check the parent is the maximum when compared to its children's. So it is a complete binary tree and also satisfy the max property. So this is a max heap. Now you can see the key features of heap trees. Heap are efficient for the priority queue operations such as insertion NQ and extraction DQ, both of which have the time complexities order of log n. In the best case, time complexity is of order of 1. Okay, the root of max heap contains the highest priority element, while in min heap it contains the lowest priority element. Heap can be efficiently represented using array, making them space efficient and easy to implement. That means it is a in place algorithm. Heap sort is a in place algorithm. What is in place algorithm? Later you can discuss. Now already can discuss parent node. The parent node of at index I, so that is equal to I minus 1 by 2, floor of I minus 1 by 2, left child of I it is 2i plus 1, right child of I is 2i plus 2. So and also we can discuss one more thing. Here it is, what is priority queue? So the priority queue means here it is a max priority or minimum priority. Okay, maximum priority or minimum priority. So priority, the number is indicated. For example, here you can consider the best example is percentage. Okay, 90 percentage. Okay, 20 percentage, which is the highest one. This is the highest one in percentage. The maximum is the highest one. So we have to construct, in this case we have to construct max heap, right? So maximum is the highest priority. For example, this is the percentage. Now you can see the ranks: 1, rank 10, rank 20. Here you can see which is the highest rank. Here 1 is the highest rank, right? So here the minimum value is the maximum priority. So in this case the minimum value is the maximum priority. In this case maximum value is the maximum priority. Maximum value is the maximum priority. So in that case how to consider the max heap? In that case you have to consider the min heap. You can construct the min heap. Okay, so minimum value is the highest priority. The number itself indicates, for example, here having 8, 1, okay, for example 12 and 3. So these are the numbers. So here I am considered minimum value is the high priority. So this is the high priority, next high priority this one, and next high priority is here, next high priority is here. Now here I am consider 8. Okay, this is a node, it is a complete binary tree, right? So it can construct the min heap, right? So because the minimum number is the high priority, so only one node is a min heap. It is a min heap. Okay, now I am taking the next element here. Here it is 1. It is not a min heap, right? The min heap means the parent node less than or equal to child. But here child is the minimum, parent is the maximum. So it is not satisfy this constraint, but it is satisfy the complete binary tree. It is satisfy the complete binary tree, but it is not satisfy the this condition, min heap property. So that here you can swap the numbers here. Here it is a 1 and here it is a 8. Alright, swap. So this is a min heap. Now you can see the 12 is there. So 12 is added here, not here, because it can follow the complete binary tree property, right? So you can add 12 here. So still it is a min heap. It satisfies the min heap property. it is a complete binary tree and also satisfies the min-heap property, right? So 3 is there. 3 cannot add here and also cannot add here and also here, but we can add 3 is here. But it is not satisfy the, it is a complete binary tree, but it is not satisfy min-heap property. But here it is a satisfy the min-heap property. Now we can see in this case it is satisfy the min-heap property. Okay, the parent is the minimum when compared to its children's. But in this case it is not satisfy the min-heap property. Okay, the parent is the maximum, the child is the minimum. So that here it is 1, here you can swap these values, here it is 3 and it is 8, it is 12. Okay, so this is the min-heap, this is the min-heap property is satisfied. It is a complete binary tree and also satisfies the min-heap property. Now how to construct here 90, 20, okay, for example 50. These are the numbers I am using. Here the maximum number is the maximum priority. The number itself indicates the priority value. So that here it is a 90 and a 20, 50 is there. Okay, for example here 100 I am consider. So 90. So here you can see maximum number is the high priority, which is the maximum number. This is the maximum number. Second priority is this one and third priority is here. Fourth priority here. So we have to consider the max-heap, right? So maximum number is the high priority. So that here I am consider the 90. It is a complete binary tree and also satisfies the max-heap property. Only one element is there. Now here I am taking the next node, here 20. It is also satisfy the max-heap property, right? So max-heap property means the parent is the maximum when compared to its children. Parent greater than or equal to child, so that it is satisfy the condition. Now I am consider the 50 here I am taking here, it is a 50. It is also satisfy the max-heap property, right? It is a complete binary tree and also satisfy the max-heap property. So here the parent is the maximum when compared to its children. Now you can add 100. Where you can add 100? Here you cannot add 100 here or here or here also. We can add 100 here because as left as possible. The node is added as left as possible. So that 100 can add here. It is a complete binary tree, but it is not a max. It is not satisfy the max-heap property because here it can satisfy. Okay, this is satisfied the max-heap property, but here it is not satisfy the max-heap property. Now in this case you can swap the values here. So 90 and here 50. Swap the values here, it is a 100, right? And also here it is 20. It is also not satisfy the max-heap property, right? It is a still complete binary tree, but it is not satisfy the max-heap property because here the parent is the minimum when compared to its children, right? So that here it is 100 and here it is 90, here it is 20, right? Here it is a 50. So now is it a complete binary tree? So this level is filled, this level is not filled, but the node is added left to right, so that it is a complete binary tree and also satisfy the max-heap property, right? So here the parent is the maximum when compared to its children. Here is the parent is the maximum when compared to its children. So this is the max-heap property. Thank you for watching. Please like, subscribe and click the bell icon for the latest notifications.